In week 2, when we introduced unitary matrices, we gave the example of a reflection in 3 dimensions as being a linear transformation that gives rise to a unitary matrix. And let's, with a prop, review what we have there. In 3-dimensional space, you could think of this right here as being a mirror. Notice that you can control this direction of that mirror with a joystick, and we might as well think of the center here as being at the origin of 3D. And then if you now have another vector in that space, and we might as well put that at the origin as well, then this subspace right here, this plane, which is the set of all vectors orthogonal to this vector that sticks out, can act like a mirror where the linear transformation gives you the vector on the other side that sticks out in the same way but mirrored. Okay. Now, the way we can visualize this on the chalkboard is by placing this in just the right way so that you're looking at this subspace that's on the edge. And then it can even be the case that this subspace has much higher dimension because it's a set of all vectors orthogonal to this vector that we're given right here, that where we view that subspace in just the right way so that we can visualize it as a line. So let's have a look at what that looks like then. What that means is that we can think of this as a mirror. We can think of this right here as being this joystick with which we control it. We can call it vector u, and for convenience we can say that vector u has 2 norm equal to 1. It has unit length. And then if you're given any vector like that, notice that u together with that vector, let's call it x, form span, the set of all vectors that you can get from those vectors is itself a 2-dimensional space, so we can view the chalkboard as being that 2-dimensional space. And then the reflected vector ends up down here. And how does a mirror work? A mirror works in such a way where this here is a right angle, and then this distance is exactly that distance. What our purpose now is to come up with a matrix that performs this transformation, that mirrors. Okay, well, let's see how we can come up with that. If we make this into a rectangle, then we know that this is the same as that. Notice that this right here is the dot product of u with x times the vector u. It's the component of x in the direction of u. And therefore, this right here, from this point right here, is also u dot product with x times u. And therefore, this vector, but pointed in the opposite direction, is the vector minus dot product of u with x times u. And then this points in exactly the same direction and has the same length, and therefore this vector right here is also minus u dot product with x times u. And therefore this vector is the vector x minus u dot product with x times u minus u dot product with x times u. In other words, this vector right here is the vector x minus 2 times the dot product of h with x times the vector u. Now, that gives us an expression for this vector, but what we want is a matrix that captures that transformation. Well, we know that a scalar times a vector is the same as a vector times a scalar. So this right here is the same as x minus u times u dot product with x. it'd be tempting to now say, oh, I can do this and factor out an x, but you can't quite do that. You can do that if you make this the identity. And what am I missing is 2. Okay, so the matrix I minus 2u Hermitian transpose is the matrix that captures the transformation that mirrors x with respect to the subspace orthogonal to vector u, where vector u must have size 1. This right here is sometimes called a reflector. It's sometimes called a householder transformation, because householder is the one who discovered how to utilize it effectively. And sometimes it's called a householder reflector. Householder transformations are going to become our friends. Many algorithms we're going to see going forward are going to use and abuse householder transformations.